All right, so it's recording and the lectures will be posted on YouTube as per usual. I hope everybody can see my screen okay. We'll begin with a brief announcement that the next phase of your design project is due on Monday, and the first thing we'll do in today's class is go over a demonstration on how you can size the reservoir that you need for your project. And by the way, I've just finished the last of the network map evaluations, and so everybody should have feedback now on how it went for phase 2. So if you log into Blackboard, you'll see the comments that I put in. Some of the comments are related to the elevation, and I think the reservoir can be taken a little bit higher in some cases, but have a look at the specific comments that I put for your network maps and let me know if you have any questions. So that's due on Monday. You've just turned in homework 9 today, if I'm remembering correctly. Let's just quickly glance at the schedule. So you turned in homework 9 just now. Your next homework assignment isn't due until the 15th of April. So you've certainly got some extra time until that's due. It's the design project on Monday, and then on Wednesday we're having the exam. So I'll give you some additional details about the exam on Monday, but the long and short of it is that I'm going to be sending you the sending you the exam by email. It'll also be posted on Blackboard. You'll take more time than I normally give you for tests. Normally our exams in class are only 50 minutes in duration, but I'm going to give you a longer window than that to take this exam, and then you'll submit the exam on Blackboard. So the format, it's going to be open note, open book. There was a question about whether the exam will be during class time. It's going to overlap the class time, but it'll be more than just the 50 minutes that we have. So I'm going to have to look at when each student is taking classes. I did an exam in my engineering econ class today, and what I did was I gave them a 3-hour window to take the test. And so, like, if we did that same thing in this class, what I do is provide you the exam at noon, and then you'd have until 3 o'clock to complete it, and hopefully within those 3 hours you'd have at least 2 to take on the test. So I'll look at when the class schedules that people are enrolled in, and we can get into the details of that a little bit later, but my intention is that you'd have at least 2 hours to take what's essentially a 50-minute test. All right, so are there any other questions related to the announcements before we start talking about reservoir sizing?
Yes, Dr. Waite. So on the phases we've been doing, can we go back and redo them, make the adjustments based on your comments?
Yeah, that's a great question. Thank you, Jeffrey. What you need to do is in the final report, you should fix any errors or mistakes that you've noticed along the way. So you don't need to submit it separately, but you integrate all the fixes to your demand estimation, to your network sizing. All of that is incorporated into the final report. Now, in addition, the final report is going to include the cost analysis part. So what you need to turn in on Monday is just the reservoir sizing, not the cost analysis. And so the final report is going to be like an updated phase 1. So it's an updated demand forecasting, an updated network map, an updated reservoir sizing if I gave you any feedback on that, and then also the cost analysis. Does that answer your question, Jeffrey?
Yes, and one more other note. I know a few of our classmates in this class has a class with Dr. Yoon after this one, time-wise, at 2 o'clock.
Yeah.
So we may have to take the test an hour earlier in this class.
Yeah, so what I might do is, if you have a class with Dr. Yoon at 2, then obviously you can't take the exam then. So I'm going to have to look at if those students are free from noon until 1. So, they'd have the 12 o'clock hour and the 1 o'clock hour to take the test. So I'll look at each person's schedule, and within that 3-hour window, I want to make sure that everyone in the class has at least 2 that they can spend on the test. Okay, now, if we go to the network map, you'll notice that up here at the top left of our network is the location where the spring is coming from. That's what the little symbol means. Is we assume that this entire development that's being prepared receives a steady flow of water to supply its demands, but we know that the demands are variable, and so there has to be a reservoir that can be drawn from during the peak demand times, so that that there's enough water available. And the figure that I've showed you before is that it's I've got two screens set up and it's projecting to the wrong one. I guess you can still see it, but the figure I showed you before is that demands are varying over time, and so in the evening hours, for example, is when you expect to see the most demand. During the nighttime hours is when you expect the least. And so the flow out of the reservoir to the town is going to be constantly changing. And what we assume is that the water comes from a source at a constant rate. And so this blue line represents the average daily flow. And so that is the average. If you integrate the area above the curve and compare it to the area under the curve, it would be equal. It's just the average of all the flow rates, and that's a pretty good assumption, because the way that drinking water production works is it's a long process that requires a series of chemical reactions and filtration processes, and so the water treatment plant isn't able to turn itself up and down quite so nimbly that it can just suddenly have a huge amount of water in the evening and then have very little water being produced at night. It's much more efficient if a water treatment plant is always operating at the same flow rate. And so a storage tank downstream of the water treatment plant, or if it's a spring or a well, whatever it is that we're producing the water with, you want to have a storage tank, and then when the demand in the city is high, you draw down from the storage tank. In a previous homework assignment, I asked you to digitize this curve. In other words, what you were supposed to do in that homework assignment is come up with a table similar to the one that you see on the screen there, where for every hour you're saying what percent of the average daily flow it is. And so the peak flow rate, the highest point during the day, when I digitized that curve, it looked like about 274% of the average daily flow. So what we want to know is, what's the average flow rate during this peak day? Not during the average day, during the peak day, because that's going to be the flow rate into the reservoir, and then the flow rates out of the reservoir are going to be variable. So here's the procedure that we're going to go through in this illustration. I'm going to go through the calculations and demonstrate for you how you can do the same thing, and then you're going to be turning it in for your design on Monday. I'm going to assume, what if the peak demand in my town that I'm sizing this reservoir for, what if it was 400 liters per second? So how big would my reservoir need to be if I had 400 liters per second is the high, and then at all the other times during the day it's some fraction of that. It's not quite as high as 400 liters per second. And so there's flow coming in, there's flow going out, and I need to know how big should the tank be so that we don't deplete the tank before the end of that daily cycle. So the process I'm going to go through is, first of all, I'm going to determine how much water needs to be coming in to satisfy that demand, and then I'm going to size the reservoir itself. Here's a summary of the procedure. First of all, we're going to look at when during the night, when the tank is replenishing, because the demands are lower at night. So at night the tank fills, because the water is coming from the source, whether it's a water treatment plant or a spring or a well of some sort. The water is going from the source to fill the tank, and that's when the tank is filling. And I'll put that at the top of the list, when the night time occurs and when it's just the first hour that the flow in is bigger than the flow out. I'll calculate the volume in and out for each hour, and then over time calculate a cumulative difference. Okay, so just to begin, what I'm going to do is I'm going to copy the data from this table with Control C. I'm going to paste it into a blank workbook. And so I'm just going to Control V and paste into this workbook, and I won't keep any of the formatting. I'm just going to have the data. So this is our reservoir sizing example. All right. And what we decided in this example, the given problem statement was we're going to assume that the peak demand is 400 liters per second. So that's something that you found out during your demand estimation, right? The bottom of your summary sheet said what's the peak demand for your development, and you probably made some adjustments to that after you submitted phase 1 based on the feedback that I gave you. And so my max flow in terms of liters per second is 400 liters per second. Oops, I need to have the labels and the number in a different cell. So there's the labels and here's the number, 400 liters per second. Okay, so to do that now I'm going to have the column I'm going to add is the flow rate in liters per second, and it's going to be the peak at 8 p.m. So I want each one of these to be based on the percentage of the peak. So it is 400 is kind of where I'm tethering it to the known flow rate. So I'll anchor that reference, and I'm going to multiply it by the percent of the peak. And so then if I drag this down through all the rest of them, I'll notice that it peaks out at 8 p.m. And so right at midnight it's 144 liters per second, 1 a.m. 136. So I know the flow in, and then I can also from that, because I know that in each hour there's 3,600 seconds, I can calculate a volume in during that 1 hour period. I'll express this one in terms of cubic meters though, rather than in liters. And so if I have 1 hour of 144 liters per second, I'm sorry, I've mislabeled that. That's a flow out because that's based on the demand. I apologize. This max flow of 400 liters per second is how much the town is using. That's their flow out. All right. Flow out and volume out. Okay, so if I have 144 liters per second for 3,600 seconds, I want to multiply the flow rate by the time period and then divide by 1,000 to convert into cubic meters from liters. So now that is going to be the volume out during that hourly period, and then I can drag that down through all of the hours. And let's also have the average calculated here, because according to the method that we're following, we are assuming that the flow in to the tank is the average of the outflows. And so we need to calculate the average outflow. So down here, I'm just going to calculate the average of the flows out. 253.5 liters per second. Average of the outflows. Okay, so the average of the outflows is what I'm going to send into the reservoir. So that's also going to be my flow in, liters per second. So it's just going to be constant. And I can drag that down through all of the hourly periods. And then there's also the volume in terms of cubic meters. So it's the flow in multiplied by 3,600 seconds per hour, and then divided by 1,000 because there's 1,000 liters in 1 cubic meter. All right, so now compare what's happening between midnight and 1 a.m. During that 1 hour period, there is 518 cubic meters of water going out of the reservoir, but 912 cubic meters going in. So obviously during that hourly period, the reservoir is getting deeper. We're accumulating water. The procedure says to find the first hour at night when the in is bigger than the out. So let's look earlier in the evening. Let's look, at 9 o'clock, how does in and out compare? So at 9 o'clock, the out is the volume, 1411. So out is bigger than in, so it's not yet filling up. Here's the 10 o'clock hour, out is bigger than in, but during the 11 o'clock hour, the flow rate in is bigger than the flow rate out. So that means it's during the 11 o'clock hour that the reservoir begins to fill. So this is a tricky thing. What that means is we have to put that at the top of the list. So the 11 o'clock hour, I'm dragging it up to the top because that's the first hour that the reservoir begins to fill. I don't need to see all those extra digits. That's just makes it a little more distracting. All right. So now I'm going to calculate a column that's the difference, ds dt. So it's the change in storage for that hourly increment. And it's in minus out. So during the 11 o'clock hour, the reservoir fills 185.9 cubic meters. During the 12 o'clock hour, we're adding an additional 401.9 cubic meters to the reservoir. So I can go down through the entire 24-hour cycle, and you'll notice that during certain periods of the evening and early morning hours, the reservoir is filling, but then during other periods of the day, the reservoir will be draining. And so let's look at that figure again. Anytime the demand is above the blue line, that means that there's more water being used by the city than the water treatment plant is producing. And so we have to be drawing down the storage that's in the reservoir. So we're using our supply of water anytime the black curve is above the blue line. And that's what we see in the spreadsheet, is that you have a negative accumulation when the demands are high, and a positive accumulation when the demands are less than the flow in. So this final column is accumulated storage volume in terms of cubic meters, and this is where we're going to look at over time how full is the reservoir. And we assume that it starts completely empty at the 11 o'clock hour, and so the first accumulation is just how much came in during that hour period. Now, at the end of the 12 o'clock hour, it's the previous hour's accumulation, so that's the cell above, plus the accumulation that occurs during this hour. And so you can see that now the total amount of water that's in the tank is the net increase during the first hour and the net increase during the second hour. Okay, so dragging it down through the rest of the cycle, now you know you did it correctly if it goes back to 0 in the end of a daily cycle. And looks like I've got an issue here because it didn't go to 0. Let's see. Okay. I wonder. Oh, I know what happened. My average changed when I dragged that cell to the top. You see where I was calculating the average? It looked in the wrong place, and so now if I readjust that so that now it's looking at the entire daily cycle, yes, now it's working. All right. So just to summarize this procedure, what we're saying is that the whole purpose of the tank is to have a supply of water to provide for the needs of the town when they're demanding water faster than the spring can provide it. The spring just is gurgling water out the side of the mountain at a constant rate. And the constant rate that we assume for your project that it's generating water at is equal to the average demand on that peak day. So there's a steady flow into the reservoir, but a variable demand coming out of the reservoir. So the variable demand you get from the figure that you digitized. The steady flow into the reservoir is just the average of all of the demands. And so the average, you can see down here at the bottom it says 253.5 is the average. Also it calculated here, but be careful when you reorder the list, putting the first time during the evening when the reservoir is filling, then that may change the average. But in any case, the tank fills, and if we go down through the daily period, it reaches some maximum and then it begins to drain again. How big should the reservoir be? We look for the largest of these. And so what's the biggest? It's right here. The required volume of the reservoir is 2439 cubic meters. And then if I wanted to put in some safety factor there, you know, I'd say let's build the reservoir to be 1.25 times this expected value. All right. A question from Michael. He asks, are the high scale and the percent of peak values the ones we use for our reservoir? You don't use my values that I came up with. You use what you developed when you did the homework assignment. I asked you to, I don't remember exactly which homework assignment it is, but you came up with something similar to this on your own. So the high scale, this percent of peak is just calculated based on the high scale. And so let me show you, that percent of peak is essentially, if we look for the biggest one here, 274, it's all of these. It's this divided by the highest one that I see. And so this decimal tells me what percentage of the maximum flow during the day. Michael, does that address your question? Okay, good. Feel free to use the microphones. That way I won't maybe... Jeffrey says he thinks it was homework 7 where I asked you to digitize that curve. Any other questions on this illustration? Okay, if I went through it too quickly for you, or if you need to refer back to it again, of course the video is recorded for the entirety of this lecture, and I think I even have a short video that's just exclusively sizing a reservoir. If you look at my YouTube channel, I have maybe a 7 or 8 minute video that's just exclusively focusing on this topic. So let's move forward now to discussing constrictions. All right, so this picture is showing, I wonder if I move this over here, I'm wondering, no, that's all right. You don't get to see these great animations I put together because if I play the presentation, it's showing up on the other screen. That's all right. So water is flowing underneath this bridge, and you can see that the piers that are put in place are effectively changing the width of the channel. In class previously we talked about expansions and contractions. So the channel getting wider, the channel getting narrower, and if you have these obstructions like the piers that are in the river, that's effectively making the available cross-sectional width of the stream less than it would have been if these piers weren't in the way. So we want to know whether the water level is going to fall or whether water level is going to rise in response to putting in these piers, which effectively reduce the width of the channel. And the reason why we don't know whether the water level will go up or down is because we haven't yet calculated the flow regime upstream. So weather conditions are supercritical or subcritical tell us whether the depth will increase or decrease. Now remember, in our previous class what we did look at was the effect on the specific energy diagram when we make the channel narrower. So this specific energy diagram, Q1 is kind of before the constriction or contraction, and Q2 is after the channel has been constricted or contracted. And by the way, a constriction means that the width specifically is decreasing. Contraction is a term that more generally just means a reduction in area. So a constriction is a type of contraction. Today we're just going to be focusing exclusively on what if there's some vertical obstruction in the channel that makes the width, which is B, less than it otherwise would have been. So lowercase q, the flow per unit width, is the flow rate divided by the width of the channel. And so when you're making the channel narrower, like effectively narrower because you put in these obstructions that makes it so that you have less flow width than you had before, you're shifting the curve up and to the right. And so there could be two different flow effects that occurs. Like if your original depth was subcritical, then the new depth is going to decrease. So here in the subcritical part of the specific energy diagram, so above the critical depth, you'll notice that on the Q1 curve we had this greater depth Y1, but then when the new specific energy diagram, which was shifted to the right and upward, to have the same amount of specific energy is going to decrease the depth. But if flow conditions originally were supercritical, meaning that our flow depth was less than the critical depth, so if we were below the minimum point on that curve, then the same amount of specific energy would give you an increased flow depth. So we needed to know the flow regime at location 1. And if it's supercritical, then that means the depth is increasing. If it's subcritical, that means the depth is decreasing. Alright, so to practice this, let's look at the specific example of what happens when we put a pier into place. Now, upstream, before those piers are in place, the width of the channel was 2.5 meters. And we're sending a flow rate of 2.25 cubic meters per second through that 2.5 meter width. And we have a known flow depth of 0.9 meters. And so downstream, when those piers are put into place, instead of 2.5 meters of flow width, since each of the piers are 0.25 meters wide, then that effectively means that the lowercase b that we have downstream, the channel width is only 2 meters, where it used to be 2.5. So here's what we're going to do. I'm going to pause from talking, and I'd like you to go through the process of upstream, calculate what's the flow velocity. So here in the steps you can see that the first step is to find V1. The second step is to find E1. Now, I've given you this version of the specific energy equation, and this is just basically adapted from what I showed you in class previously, where the specific energy upstream is equal to downstream, and that can be in terms of the velocity head being V, it can be in terms of the velocity head in terms of Q or lowercase q, or some combination of those. So what I did was I took the first part of the equation here, so this, the energy at 1, is equal to the energy at 2. And now in this example, the reason why we did that is you can find the velocity at 1 directly, but you're not going to at first know what was the velocity at 2. But you will know the flow at 2. So I'm going to pause for a moment, calculate the velocity at 1 with the given width, the given depth, the given flow rate. So remember, Q equals V times A. So find V1. Then, once you know V1 and you have a given flow depth, calculate E1. So that's the left-hand side of the energy equation, and then use that E1 to solve for Y2. The only unknown on the right-hand side of the equation will be the new flow depth, and that'll end up being a cubic equation where you're going to have to identify which of the routes to select based on weather conditions upstream are supercritical or subcritical. Alright, so I'm going to pause for a moment. You chug through the calculations. If you have any questions, feel free to chime in with the audio, or you can type them in the chat box. And of course, we'll come back and I'll show you the solution. All right, let's take a look at some of the calculations so far. Okay, so the first thing that I suggested you look at was the velocity at location 1. And so Q equals VA, therefore V is Q divided by A. So if the given flow rate is 2.25 cubic meters per second, and then the channel is 2.5 meters wide and 0.9 meters is the flow depth, then that means our velocity at location 1 is 1 meter per second. Now that's before the constriction. So that's upstream of the constriction is where the velocity is 1 meter per second. And so how much specific energy is there at location 1? It's going to be the depth plus the velocity head. And so since the depth is 0.9 meters, then we also add in the velocity head component. That means that the total amount of specific energy upstream is 0.951 meters. So that gives us both the velocity at 1 and the specific energy at 1. Now to find out what is the new depth downstream, where the constriction occurs, we can set it equal, the specific energy at 1 is equal to the specific energy at 2. And since I don't know what the velocity is going to be at 2, but I do know the flow rate, that's why I chose to have the velocity head in terms of Q squared divided by 2GA squared. And so you can see I've made the substitution for the cross-sectional area is Y2, so that's the new depth downstream, multiplied by the width of the channel. Now that's the effective width. That's the width that water can flow through. There's obstructions in the way for 0.5 meters, since each of the pier columns is 0.25 meters wide, and there's 2 of them. And that means that the effective flow width is 2 meters. So if I substitute in the known numbers for that, then 0.951 is the specific energy at 1, and I'm solving for Y2 on the right-hand side of the equation. And just go through the algebra of rearranging this equation, combining like terms. So multiplying each term in the equation by Y2 squared to get it out from the denominator under that term, and then rearranging the equation in terms of a cubic, where on the right hand side it's equal to 0, and then if you put it into the calculator you can find that there are 3 roots, a negative root and then 2 non-negative roots, one of which corresponds to supercritical conditions and another flow depth that corresponds to subcritical conditions. Now you may have noticed that up at the top of my paper I calculated the critical depth, and there's a couple of ways for us to determine the flow regime upstream. So remember, which of those 2 routes we select downstream depends on what was the water doing upstream before the constriction occurred. Now the critical depth, based on the flow per unit width for this rectangular channel and G, the critical depth is 0.436, and if we compare the given flow depth, it told us that the flow depth originally upstream was 0.9 meters. So conditions upstream are subcritical because anytime your given flow depth is greater than the critical depth, that means subcritical conditions. So one way I know it's subcritical is comparing critical depth to the given depth, or I could calculate the Froude number, and I also did that. So here's the calculations for the Froude number. Initially, upstream at location 1, the Froude number is less than 1. So anytime the Froude number is less than 1, that's another indicator that the flow regime is subcritical. And so since I had subcritical at location 1, then that tells me I should select this route, the deeper of the two depths, which is associated with slower moving velocity, greater depth. And so the new depth after the obstruction is put into place is 0.865 meters. So it's another one of those kind of gee whiz type things where if you're thinking about what's happening when water has to get around an obstruction, you maybe would have expected that it would get deeper because of the decreased flow width. You think if you're putting in an obstruction, that's maybe going to cause the water to get deeper. And if you made those obstructions progressively wider and wider so that it obstructs the flow and causes pooling upstream, then yes, the water depth would increase upstream of the obstruction if we made these too wide. But these, we haven't gone beyond the maximum flow that can be accommodated without pooling upstream. And so what that means is that the depth at the constriction, at location 2, the depth decreases, and so the velocity had to have increased to make that happen. So the way that continuity is honored, that flow in equals flow out, is just that the velocity at location 2 is greater than it was prior to the constriction being put into place. Okay, so that's just another supporting example that goes along the lines of specific energy diagrams and how we find out what's the flow depth when there's something like a step down or a step up or a channel getting narrower or getting wider. We usually find that we solve the cubic equations and then we decide which route to select based on the flow conditions before that obstruction occurred. Are there any questions on this example before we conclude for today? All right, well, if not, I'll just remind you of the announcements that the design project submission you have for reservoir sizing is due on Monday. I'll send you the link to that short video that just summarizes what I showed you today, the procedure that summarizes how to size a reservoir. I'll send you the link to that. I'm also going to look into everyone's schedule and identify a time when you'll have at least 2 hours to take the exam, and we'll talk about that on Monday. But in the meantime, if you have any questions based on the feedback I gave you for project phase 2 or any questions on the examples we went through today, feel free to send me an email or give me a call. Looks like a sunny day out there, so I hope everybody has a good day. Maybe there was another question here. Yeah, Maggie's surprised we're ending early. We are. We are ending early. So enjoy it. Go enjoy some of this sunny weather and take care, everybody.